If we're doing Galilean transformations, then we kind of have this setup where we have f of x and f of x prime, where this is an observer stationary, and this is a moving frame. So the frame has a velocity, which is going to change the x-coordinate. As you can see, we have the regular x-coordinate, and then this one gets shifted by some velocity. And the times are going to be the same because this is just Galilean transformations. We're not really doing special relativity yet. It's just like regular sort of like walking down the airport on the moving platform and stuff. But what we're going to do is we're going to take some derivatives. So we got the derivative here, so dx over dt, and then that's going to be equal to this dx prime over dt plus a v, since this is going to cancel out. Cool thing is dt equals dt prime, so this little term here just kind of turns into this. This is basically going to either say we have u prime, so what a u prime, this is a particle, okay, so this is like a particle mover. So kind of distinguishing the velocity of the particle and the velocity of like the frame. So you're kind of distinguishing between the velocity of the person sort of walking on the platform, which is the particle, and then the moving platform itself has a velocity, if we're thinking about that airport. So we have a dx over dt. The regular one just gives us u, and then this one with prime just gives us u prime. So the combination of u prime plus v gives us u. And so this is just some basic equations that gets you started. But then what we want to do is we want to try to figure out these partials in terms of time. Uh, if we're looking at partials of space, like dx, that's actually just equal to dx prime. So you can just substitute those straight away, the spatial ones, right? If we're doing the Galilean relativity again. But if we're doing the time ones, then um, we have different partials and different totals. So um, let's start with the total derivatives first, because usually kind of understand derivatives. And we just talked about these velocities and stuff. So I guess we'll kind of start there. The idea is that we're taking a derivative of the actual frame itself. So we kind of have two different types of derivatives. We have the regular derivative, which tells us the dynamics of the frame, and then we also have the partials, which basically scales um, it scales the partials. Like if you take a partial of this frame, then it will scale the other partials for the other frame. As you can see, you kind of get the scaling factor for these partials. Um, so that's kind of interesting. So we're basically either scaling partials or we are figuring out what the dynamics are. So we're taking derivative of f, which means that we're kind of interested in df over dt, but notice this is a partial, and that's because we have two of them. We have the space and time partials here. But then what we're going to do is we're going to attempt to sort of cancel out this term in a way. Of course, we're doing it with a partial and then a total here. But if we try to do that and sort of pretending that these kind of cancel, though they don't, but if they would, then you'd be left with this df over dt. So we're sort of trying to take this time partial here, so we're kind of left with that, canceling this out, and we're left with df over dt, kind of. Although we're not supposed to cancel this, we're supposed to really solve them, meaning this thing right here, if you take dt over dt, that's just equal to 1. And if you take a derivative of x, well, remember we already explained that it was u. It's just the particle motion. It's just the person like walking on the thing. It's the velocity of that. So so that's the first step here. And of course, once we convert that over here, I actually kind of switch this around. Should sort of be a dt on this left side is left over. That's this, and I took away the f just to make it a little bit simpler. And then we're left with u times dx over d over dx. So that's this times that. All right, so this is just kind of decoding what we have here. Um, I don't like it, but I guess we're gonna switch it around again. So here we're just kind of doing it the exact same thing in the primed reference frame. So it's nothing too crazy. We're sort of just taking a chain rule. So we're again sort of canceling out. Uh, we take a little partial of t prime here. Then we kind of cancel it with the the dt prime here, and then we're sort of putting the total derivative here. So we're kind of flipping a partial to a total. If you kind of convert the partial to total, it's kind of interesting. So that's a sort of another way to think about it. It's kind of like here we're going from a partial to total conversion, whereas over here we're trying to doing like the partial of this thing switching to the partials of this thing. If that kind of makes sense, we'll see. We'll see about that in just a second. Uh, but yeah, so here we're going from the partial to the total. As you can see, it's a nice little conversion here. We're just going back to 1. Here we are taking the derivative and it turns to u prime. And there we go. And here what we could do is we could substitute this. So you can actually just flip this from dx prime to just to a dx. You can just go ahead and say, oh, well, that's the exact same thing. That's pretty cool. And over here, though, on the time side, we already determined, oh, actually, we didn't determine it already. We have to figure out what dt prime is. So dt, this partial t and partial dt prime here, these are not the same. We've sort of figured out what dt, the total dt, and the total dt prime here is. These two, let's go ahead and switch over to the next thing. I know this is very confusing. This is why it's actually my like 4th or 5th time filming this, although I finally kind of get it. So let's just get through this. This is super important. That's why we're doing it. Anyway, we got this partial f, partial t now. And in this case, we're going to try to essentially convert these regular partials into prime partials. And the way we do that is we're sort of, we're taking the prime partial, and then we're canceling out that dt prime, and then we're going to take our partial t, which is kind of what we are looking for. We're trying to figure out what's changing here. And over here, we kind of do the same thing. So we're just taking the chain rule, partials of the primed coordinates, so that way we can kind of convert it, and we're sort of cutting that out, and we're left with sort of these primed partials in the end. Because what we do is we're solving for this. This cancels out to 1. This cancels out to negative v. Why is it negative v? Well, maybe it'll be easier to look at why this is v, because it's the same principle. If we take a partial of x or partial of x prime, then what we do is we look at this equation. And if we take a partial of x over partial t, then this term goes away, and then we're just left with positive v. Of course, if we're doing the partial for the x prime, then we're going to put all this stuff on the other side. It becomes negative v, and then, of course, we just get negative v. So that's basically what we're doing here. We're taking some partials of x or x prime and getting this negative v terms. This stuff is, again, going to cancel out to 1, and so this is how we can sort of determine what this primed partial is and what this, sorry, what the prime partial and unprimed partials are. So now that we know what the unprimed partial is, d over dt prime is actually equal to this, which means that anytime we have a d over dt prime, which means here, we could just go ahead and plug that right in there. And the same thing over here, we can plug that right in there. Just kind of take this and plug it right in here. So I say substitute right here. Although this spatial coordinate, again, you can just flip it right back and forth between the prime with no need to make anything complicated. So hopefully this clears up the this matter, because this stuff is very, very strange. I feel like sort of the best way we can consider this is conversion factors. We're trying to convert sort of we're taking partials and Well, I really is we're taking totals and making them into partials here. I guess that's kind of what we did right here. Flipped it around really, because notice how we input it with a total. So we have this right here, and then we got like a, so we input this total and we output these partials. And here we input this partial and then we output these prime partials. So we're doing little conversion factors and we're scaling partials both times. All right, so that's kind of interesting stuff. Thank you all so much for